Hello and welcome to this film, which is all about reaction quotients, and hopefully by the end of it you'll understand what we mean by a reaction quotient, and you'll be able to compare the value of a reaction quotient to the value of an equilibrium constant and use that comparison to predict what changes might occur in a system that isn't at equilibrium. Okay, so first of all we'll have a look at what reaction quotients are. Now hopefully by now you know what an equilibrium constant is, and so if I explain this quite quickly, it will hopefully make sense. So if we've got a reversible reaction where reactants are turning into products, then we can express the reaction quotient, which we call Q for short, as the concentration of the products over the concentration of the reactants. And if we're being a little bit less general than that, but still being quite general here, so if we had perhaps A and B as our reactants turning reversibly into C, then we could say that the reaction quotient Q, or an expression for it, would be the concentration of C divided by the concentration of A multiplied by the concentration of B. And if we had a look at a reaction that had some coefficients in it, let's say 2 A's turning into a B and 3 C's, then the reaction quotient would be the concentration of B multiplied by the concentration of C cubed, because of this 3, divided by the reactants, which is A, but in this case squared because we had a stoichiometric coefficient of 2. Now you might be thinking, well, hang on a minute, this sounds awfully familiar. This sounds just like what we learned about equilibrium constants. Well, it is rather like that, except that you can only calculate an equilibrium constant at equilibrium. So you could calculate the concentration of products and divide it by the concentration of reactants at any time. But if you were doing that at equilibrium, then you would be calculating K. You'd be calculating something called the equilibrium constant. If you did it for a reaction that was not at equilibrium, you'd be calculating Q. So that really is the only difference between K and Q. Now, if they're practically the same thing, but with just that small difference that Q is about a system that is not at equilibrium, and K is for a system that is at equilibrium, well, what can we do with these two things? Well, hopefully we can compare the value of Q to the value of K. Now let's look at 3 different situations that might arise. Okay, Q could be bigger than K, Q could be smaller than K, or Q could be equal to K. So we have calculated Q. Remember, we can do this at any time, and we're going to compare it to the value of K, which is what the ratio of products to reactants will be at equilibrium. And you can see here the expressions for them are basically the same, right? So not wanting to labour that point too much, but we calculate them in exactly the same way. It's just that Q can be calculated any time you like, and K can only be calculated at equilibrium. So in other words, if we calculated Q and the system wasn't at equilibrium, then we could say which way it's going to go in order to get to equilibrium. Okay, so if Q was bigger than K, that means that this ratio here is bigger than this ratio here. In other words, there are more products or fewer reactants than there would be at equilibrium. So if we found that Q was bigger than K, then the system would shift towards the reactant side in order to reach equilibrium. Okay, so it would go to the left towards the reactant side. If Q was less than K, then this ratio here is smaller than that ratio there. In other words, there are fewer products or more reactants than we would expect at equilibrium. And in that case, what would this system do? Well, it would move toward the product side. In other words, it would shift to the right so that it could establish itself at equilibrium again, with the ratio as it should be at equilibrium. And if Q is equal to K, and this ratio is exactly what it would be at equilibrium, then we can say the system is at equilibrium and it won't shift at all. Okay, so hopefully now you understand what we mean by a reaction quotient. And as we've said, it's very, very similar to an equilibrium constant. And you've seen how, by looking at the value of it and comparing it to the value of K, we can decide which way a system that is not at equilibrium will move in order to get to equilibrium. Now, as usual, if you've got any questions or comments, then please feel free to come and see me or to post a comment on YouTube.